Okay, today we're going to be talking about drag force. And drag force is going to be a force that's going to resist motion. So it's going to be in the opposite direction that motion is. So a lot of times when we think about drag force is somebody dropping like a parachutist going down jumping from a plane, coming down here. If it's moving this way, the drag force is going to be the opposite. Another example of drag force is a truck on a highway. A lot of times you see this nice curved thing on the top of a big huge truck, and what that does is that decreases drag force. So a truck going down a highway is moving in this direction. Drag force is going to be pushing it in the opposite direction, and it slows down its motion. Okay, the official definition is going to be the forces produced by a fluid that acts on the object moving through the fluid. So this is the forces come from the fluid, and it's acting on the object as it's moving. It has to be moving. There's no drag force if something's not moving, and it's going to be coming from the fluid. Now where we get confused is the word fluid. Right here, we have to remember that fluid can be a liquid or a gas. So a lot of times we think of water as fluid, but air is also fluid. It's a liquid, it's a gas, and therefore it responds the same way. So this could be a submarine going through water is going to have drag force where the fluid is the seawater, or it can be a parachutist jumping out of an airplane and the fluid there is going to be the air. So we're going to be talking about any type of fluid. Okay, the things that depend on the drag force, meaning how strong that drag force is going to be a couple things. First, it's the velocity of the object. So the slower you go, the less of a drag force that you have. The faster you go, you're going to have a larger drag force. Okay, so if you ever notice motorcyclists on the highway, they hunch down, and one reason they do that is because they can decrease the drag force, and that gives us the shape of the object. So somebody who's sitting straight up is going to have more drag force, and a motorcyclist hunched over is going to have less drag force. So another example would be if you're riding down one of those water slides at the water parks, a lot of times you lay down instead of sitting up, because when you sit up you have more of a surface area contacting that drag force. If you lay down, you become less. And now what happens is it's the cross-sectional area. Okay, so if you have a box right here, the cross-sectional area would be this whole box. If it's a three-dimensional box, all we're worried about is what the air is touching going right that way. A parachutist, if it's a three-dimensional parachutist flying in the air like this, it would just be the cross-sectional area of that parachutist. So if the parachutist got into a small ball, the cross-sectional area is much smaller than this larger area here. So that's the shape of the object. It also is dependent on the properties of the fluid. So for instance, air is going to have a different response to drag force than water would. And we also have the issues of salt water versus fresh water. They have different properties. So if we had something that was dropped in a vat of oil versus a vat of water, it's going to sink faster in a vat of water, and oil has a larger drag force. Okay, so those are some things that the drag force depends on. Okay, well, as the object's velocity increases, so we have this person jumping out of a plane. When they first jump out of the plane, they're dropping, so they have an initial velocity of 0. So our initial velocity is 0. Well, what happens as they're dropping, and we learn this using our gravity lab, is that the ball drops faster and faster. It's accelerating. Well, the same thing happens to this guy. So as he's dropping, his velocity is increasing. Okay, so as the object's velocity increases, the drag force is increasing. The faster they go, the larger the drag force. What happens is it increases until a certain point. Once it reaches this certain point, the drag force and the force of gravity are equal. So right here, if we were to draw a free body diagram of this parachutist jumping out, we have the drag force that's up and the force of gravity that's down. These become the drag force increases until they're equal. Well, when they're equal, what happens is force drag equals force of gravity, and that means that the net force has to be 0. This magnitude is equal to that magnitude. When our net force is equal to 0, that means our acceleration has to be 0. So that is a key to drag force. The acceleration is 0. You no longer are accelerating. So at the beginning, what is the acceleration of someone jumping out of a plane? It's negative 9.81. Well, once you hit a certain point, the acceleration goes to 0. This point is called terminal velocity. And sometimes it's referred to as V and a little t underneath it, terminal velocity. This is the velocity that something falls where there is no acceleration. So if we were jumping out of an airplane, or even the gravity lab that we did, if we did it at a higher up value, if we could get a delta Y that was large enough, those balls would drop, and then it would be a certain point where they would no longer be accelerating and dropping at a constant velocity, which is terminal velocity. Okay, so let's try an example. So we have a skydiver of mass 80 kilograms jumps from an airplane and reaches terminal velocity. So the key here is that he reaches terminal velocity. So right away we know that A, acceleration, is 0. What is his drag force at this time? Well, the given is his mass. We know his mass is 80 kilograms. What's unknown is his drag force. We're asking for what's the drag force. So we know from our free body diagram that because it's terminal velocity, that Fd has to equal Fg. So Fnet is Fd minus Fg, and Fnet is mass times acceleration, but this has to be 0 because it's terminal velocity. So this Ma goes to 0, and we do a little geometry or a little algebra here, and we know that the drag force has to equal the force of gravity. Force of gravity is mass times gravity, and we're just going to plug in our mass times our gravity, and we end up that the drag force is 78.4 newtons. Now this doesn't mean that the object isn't moving because A is 0, it just is no longer accelerating. It's going at a constant velocity down to the ground. Okay, so if we were going to take the same bit of information now and create a motion diagram, remembering that the motion diagrams are the dots, what's it going to look like? So we have this person that's jumping out of a plane, and they're going to start right here. Well, what happens, the motion diagram is going to show distance. Well, he has very little distance, and then the velocity is going to be increasing. Okay, so right time, this is showing increasing velocity. Okay, so we have increasing velocity. Well, then what happens? We reach a point right here, and this point's going to be terminal velocity, v sub t. Once it's at terminal velocity, it's no longer accelerating. That means that it's going to be going at constant velocity. So now, from now on, it goes at constant velocity. And this distance between each one of these is the same. So this is constant velocity. And that's what that would look like on a motion diagram. Okay, so don't forget to do the Edline assignment for tonight, and we'll see you tomorrow in class.